check out this awesome artist sometime. He's actually an artist and a mathematician named M.C. Escher, and he's made some pretty incredible things. I thought as we started our lesson on spheres that this would be a great picture. This is his self-portrait. And of course, a sphere is just a round ball. Let's get some vocabulary out of the way. Just a round ball, you know it, you love it, and the radius is constant all the way from any point from the center out. It's always the same radius. Now, when you take a half a sphere, chop it in half right through the center, you get what we call a hemisphere. And we see this on the Earth, like the Western Hemisphere, the Eastern Hemisphere, Southern, all those. And one last thing that's going to be important as we do our study here is the definition of what we call a great circle. And a great circle is simply the biggest circle that you can draw on the surface of a sphere. Now, we could draw a lot of circles on a sphere, but there's one that's going to be bigger than any other, and that's the one that shares the center with the sphere itself. So you can see up here I can draw lots of circles, but this circle is going to be smaller than the one that goes right through around, cutting it basically into two hemispheres. A globe is a good way to see that. On a globe, one good example of a great circle would be right there, the equator. That's the biggest circle we could draw on this sphere, is the equator. But not to be outdone, any line that we could draw around on the biggest circle, so like these lines of longitude here, this will be coming around in the back, coming back up, that would be a great circle. So there's a lot of different great circles going every direction. The important thing to remember, though, is it's the biggest circle you can get. And why is a great circle so important? Well, it comes into the formula for finding surface area of a sphere. The surface area of a sphere can be found by taking 4 great circle areas. So it's going to be 4, and then a great circle would be the area of a circle, pi r squared. Now, we usually don't put the parentheses in there, but I'm going to, because I want you to notice that this is the area of a great circle. And that's going to be a good thing to know when we come into some problems. 4 great circle areas is equal to the area of the surface of the sphere. And then we're also going to cover the volume while we're here. The volume of a sphere is found by taking 4/3 of pi r cubed. One important thing to remember is that the cube helps you remember the units are cubed. And up here in our surface area, we get to square the radius. Areas are always square units. So keep those things in mind. Let's do some examples. We're going to just find the surface area of this sphere. So let's start with our surface area formula. 4 pi r squared. And we just go plug straight into this. So 4 pi comes down, and then pulling from our diagram, the radius is 5 meters. We're going to square the 5 and calculate that out. So let's start with squaring the 5 to 25 multiplied by 4. Get 100 and bring down that pi. So we've got 100 pi square meters. That's our surface area. A word problem, yes. Find the surface area of a sphere if its circumference measures 14 pi inches. So let's just write down our surface area formula. And I think it's going to be helpful if we get a picture of this. So I'll try my best, but we're going to draw a sphere. I'm no artist, but here's how I do it. I'm going to draw a circle, and then I'm going to take another circle. It's going to look like an oval. This is going to kind of show like an equator, or really a great circle coming around. It shows this illusion of depth as I go dotted in the back there. Okay, so that's what we've got. There's the center. Now we're told that the circumference of this sphere measures 14 pi inches. That's the circumference. So that's that same distance around that I went all the way around here. The circumference of a great circle is equal to 14 pi inches. That doesn't tell me much. I need the radius, don't I? I need the radius of this sphere. So how could we figure out the radius of the sphere? Only knowing that the circumference is 14 pi. Well, let's remember that the circumference of a circle, a great circle in this case, is 2 pi r. So substituting that 14 pi in the spot for circumference and bringing down the rest, I can solve this for the radius if I just divide off the 2 and the pi. So let's divide by 2 pi on both sides. And nice thing is I get to cancel the pi. I get to cancel it over here also. The 2's are gone also. So it's just 14 divided by 2, or 7. So the radius of this is 7. Then I'm ready to go put it up in that formula. So let's bring out what we know. We got 4 pi, and the radius again is 7. We've got to make sure to square it. What does that calculate out to? 196 with pi still in there. And then our unit. What was our unit on this? Back up here, inches. So this is a square inch for area. Now things change a little bit when you start cutting spheres up, so I want you to be paying close attention on this example. We've defined the surface area of this hemisphere, but let's make sure we're breaking it down correctly. There is this curved surface, and the curved surface, for now I'm just going to call it a dome. But there's also a floor or a base circle. And so I need to do this in 2 pieces. So the surface area is going to be whatever that dome or that roof is, but then I need to make sure I add in a base floor. Well, how would I figure out the dome? Let's start with that. The dome is going to be 1/2 of our total surface area of a sphere. So half of 4 pi r squared. In other words, that's just going to be 2 pi r squared. The floor, though, the floor is going to be just a circle, so that's equal to pi r squared. Okay, so filling in what we know, on the dome we have 2 pi r squared, and the base floor is just pi r squared. Those can be simplified. Those are like terms. I have 2 pi r squared plus 1 more pi r squared. In fact, let me put in a 1 there. 2 plus 1 makes 3 pi r squared. So, as a hint to you, for some of your problems, and you want to write this down, this is 3 great circles. All right, let's plug in what we know. So we're going to just go for it. We've got 3 pi times our radius squared. Our radius here is going to be half of that 9, or 4.5. We're going to square that. Okay, now let's crank it out. Comes out to be 60.75 pi. Cubic centimeters. Now, you're going to find as we work some problems that knowing that that hemisphere is just 3 great circles, or 3 pi r squared, that's kind of a new formula. That'll actually help you. Nice shortcut. All right, let's turn our attention to volume now. We left that formula kind of in the dust, so let's recap it. It's 4/3 of pi times the radius cubed, cubic for volume. Let's go and plug in what we know. Bringing everything down, I'm going to put in 8 centimeters for the radius and calculate that. Now remember, 8 cubed means 8 times 8 times 8, although you should have a button on it, your calculator, for cubing. Hunt for it. If you can't find it, I'll help you out. But go ahead and multiply 8 cubed by 4 and divide it by 3. And that comes out to be 682.6 repeating pi, because I didn't put that in my calculator. So my volume is 682.6 repeating pi cubic centimeters, if I want to get it all exact. Final example is an application, and this is true to life. To make a steel ball bearing, the things that come in your your skateboard wheels that make wheels run really nicely, what they do is take a slug, which is usually in a cylinder shape, and they heat it down, they melt it down, and then they mold it into a sphere to make that ball bearing. And they use it all, so it does get the same volume. So we're going to find the radius of this ball bearing that's made from this slug. In order to do so, we're going to have to figure out the volume. That's the only thing that's equal about these two things, is that their volumes match. So let's start with the volume of our cylinder. Now you're going to have to remember the formula for that. I remember it's pi r squared times the height of the cylinder. So that's pretty straightforward to plug in. The radius of this is just the 1 centimeter, and it's 2 centimeters tall. So that comes out to just be 2 pi for the volume. Now this cylinder has the exact same volume as this steel ball bearing. So the volume of the ball bearing is a different formula since this is a sphere. This is our new formula, 4/3 pi r cubed. But what we're going to do is we're going to take this volume, this 2 pi, and we're going to use it as the volume of the ball bearing. So 2 pi is equal to our formula, and with that we'll be able to figure out the radius. Now, there's a little bit of technical work to happen here. How do we get that radius all alone, or how do we isolate it? Let's start by taking advantage of the fact that we can divide the pi out of this whole thing. So let's cancel pi from here. It cancels from here too, and that just brings us to 2 is equal to 4/3 the radius cubed. Now, in order to get rid of the 4/3, I say we multiply by the reciprocal. So let's times it by 3/4, do it on both sides. And that'll let us cancel the 4's and the 3's. And I'm running out of space, so I'm going to come up here. Okay, on this side we get 3 times 2 and divided by 4, and that comes out as 1.5 equal to the radius cubed. Now, this is the first time that we've had a cube involved. How would you undo a cube? Well, this is how it works. It's just like undoing a square when you take the square root, except we want to know the cube root. What times itself again? And so that looks like this. There's going to be a little cube, a little 3 on your radical. And you're going to do the same thing to both sides. Now, your calculator has a button that will take a cube root of a number. On this side, it just cancels, so you just get r, but you have to find in your calculator the cube root button and use it to find the cube root of 1.5. Give it a try using your own calculator, and you should come up with about 1.14 if I'm going to round it to the nearest hundredth. Okay, now this is going to be centimeters, and that'll be the radius of our ball bearing. This is an important example for you to know how to use on your calculator. Please ask me a question. Put a big question mark by this if you can't figure that out, and I will help you in class with that. But that's the deal with spheres. It's pretty straightforward. You just have to know the radius, and you can use the formulas.